Hi, hello to everyone. My name is Dr. D. Sudhakar, working as Professor and Head of Mechanical Department at Siddhartha Institute of Science and Technology, Puttur. Today, we are going to discuss about this electrochemical machining process. In that process, what are the equipments where we are using for the machine for running of these equipments, and what are the major components present in the electrochemical machining process? The major components present in this electrochemical machining process are like number one is power supply system, and then electrolyte supply and cleaning system, tool and tool feed system, workpiece and work holding system. The first one is power supply system. The second one is electrolyte supply and cleaning system. And third one is tool and tool feed system. And then fourth one is the workpiece and work holding system. Now, one by one, we are going to discuss about all these major components which are involved in this electrochemical machining. So, this is the diagram, schematic diagram, represent or indicate, gives the more information about what exactly the components present in this electrochemical machining process. Means here the power supply means the brief information is like a power supply. Means here we are going to the tool is DC power supply. We are going to supply that it is the tool is the workpiece is connected to the positive terminal and acts as a anode, and here the tool is connected to the negative terminal and it is acts as a cathode. And then again, so next point is the electrolyte supply and cleaning system. See, this is the electrolyte container. Okay, and here from here we are going to supply towards this tool. In between this tool and workpiece, we are going to gap. We have to maintain a gap, small gap between the tool and workpiece. That is the inter-electrode gap. Here, the chemical electrolyte will come into the picture, and because of this chemical because of this chemical reaction, some machining will be takes place, and whatever the material is removed, and whatever the exactly reactions we have discussed in the last video, because of those reactions, the sludges and precipitation will be formed. Those will be collected here, and again we are going to filter those sludges properly and collected in this container, and the filtered electrolyte will be passed again to the container, and then it is going to recirculate like this. That is the electrolyte supply and cleaning system. Next, tool and tool feed system. This is the tool actually. The tool is the surface is coated with the chemically resistant material. So because of these sites, no machining will be happen, and the tool will be through this tool. We are going to supply this electrolyte, and how we have to maintain a constant inter-electrode gap in between this tool and workpiece by means of the servo control mechanism. That is also we are going to discuss. And what are the tool materials we have used in order to prepare this tool? That is also we will discuss in this way. And next one is workpiece and work holding system. So this is the workpiece. This is the workpiece. And this workpiece is properly we have to fix on this work holding system. And about this one also we are going to discuss in those. Now we'll discuss about the power supply. What exactly the power supply we are going to using in this electrochemical machining process. See, during this electrochemical machining process, a high value of direct current means DC current we are going to use. It may be like approximately 40,000 amps, and a low value of electric potential means the voltage, low voltage we are going to supply, that is 5 to 25 volts across the inter-electrode. IEZ means inter-electrode gap, means the gap, whatever the gap we are going to maintain in between the tool and workpiece, that gap is called as a inter-electrode gap. The highest current density is achieved so far is around 20,000 amps per centimeter square. So even though you supply this much, but more or less nearly 20,000 amps per centimeter square, this much amount amps we are going to concentrating or placing on this each per centimeter square. Hence, with help of a rectifier and a transformer three-phase AC is converted into a low voltage and high current DC. The silicon controlled rectifier SCRs are used both for rectification as well as for the voltage regulation because of their rapid response to change in the process load and their compactness. The voltage regulation of plus or minus 1% is adequate for the most of the precision ECM electrochemical machining works. Now coming to this electrolyte and power, electrolyte supply and cleaning system means how we are going to supply this electrolyte to the machining zone in electrochemical machining process, and after machining how we are going to collect those electrolyte and how we are going to clean those electrolyte properly, and how we are going to remove those sludges and unwanted materials from the electrolyte, and how we can recirculate again to the machining zone, and all those things we are going to discuss in this talk. The electrolyte supply and cleaning system consists of so many components like pump, filter, pipings, control valves, heating or cooling coils, pressure gauges, and a storage tank, or it is also known as a reservoir. So these are the components which are involved in this electrolyte supply and cleaning system. The electrolyte supply ports may be made in the tool. So in the middle of the tool, we are going to supply this electrolyte for the proper reaching of this electrolyte exactly at the machining zone. For that purpose, we are going to use this. We are going to create a hole at the inside the tool. And one more thing is, it may be through the workpiece. It maybe there are different ways to supply the electrolyte to the machining zone, through the tool or through the workpiece or through the fixer. Depending upon the requirement, depending upon the complexity of the workpiece, we are going to supply this electrolyte in different methods. But in this condition, in this diagram, what we seen here, see in the in between, in the middle of the tool, where we have created a port. Through that port, we are supplying this electrolyte to the machining zone. Even we can supply at the from bottom to top or from the side through the nozzle, like different methods are there, but here we are using at the from the middle of the tool where we are creating one port. Through the port we are going to supply the electrolyte to this machining zone. A smaller inter-electrode gap means I already told you, inter-electrode gap means whatever the gap we have maintained in between the tool and workpiece, that gap is known as inter-electrode gap. It should be very, very small. Usually is in the range of smaller than 1 mm gap we have to maintain. Manually, it is very much difficult to maintain such a small gap in between the tool and workpiece. For that one, we are using a servo control mechanism. By means of the servo control mechanism, we are going to monitor the gap constantly, and we will maintain, and we have maintaining the exact gap 1 mm between the tool and workpiece. So if it is more than the 1 mm, automatically it will affect on the surface finish and work and accuracy, the RM metal removal rate. That's why we should maintain a less than 1 mm gap, so that we are going to achieve a high metal removal rate and very good accuracy. So for this purpose, a smooth flow of electrolyte should be maintained, and any block in such small gap by means of any particles, it's very difficult, and the metal removal rate will be reduced and accuracy will be reduced, so that we have to maintain a gap. So there should not create any block, or the electrolyte should be properly flowed through the tool, and it should be reach the machining zone properly without any block. Hence, the electrolyte cleanliness is very much important. So if the electrolyte is not cleanliness and not having any cleanliness, and it is having any particles or any chips, or if any unwanted particles are present in the electrolyte, what will happen? Automatically, there is a small, these particles may clog or block, or it may struck in the machining zone as we are maintaining a very small gap between this tool and workpiece. See, this is the very small gap we are maintaining. That that gap is very less. That the what is that? What one less than 1 mm gap. So because of that one, so as it is very small gap, if any particles are coming through this port, automatically it will block, so that proper machining will not be takes place, and the it will affect on metal removal rate and surface finish. So that because of the reason, what exactly the point we have to remember is the electrolyte cleanliness is very important. So it is normally done with help of filters made of stainless steel or monel or any other anti-corrosive materials. Why we have to use these anti-corrosive materials as a filter materials? Because this electrolyte is a corrosive proper. It's having some corrosive nature. That's why we should not use any materials which are affected by these chemicals. Then it should be ensured that the piping should pipings whatever the so while supplying this electrolyte from container to the reservoir to the machining zone, and from machining zone to the what is that where we are going to filtering those electrolyte. For all this one, we need some piping system. So while supplying this electrolyte to this machining zone or collecting this electrolyte from machining zone to the filtration chamber, those piping should not interact or should not be a corrosive material. Corrosive material. It should be anti-corrosive material. It should not affected by the electrolyte. So such type of piping system we have to use. So you should not create any scales or if any scales are formed inside this piping system, automatically some pieces are broken and piping the entire piping system will be damaged. So that the piping system is therefore made of, it may be stainless steels or glass fiber reinforced plastics or plastic lined mild steel or similar other anti-corrosive materials are used for this piping system to supply the electrolyte from electrolyte chamber to the machining zone and to collect that electrolyte from machining zone to the filtration chamber. The required minimum capacity of electrolyte tank is 500 gallons for each 10,000 amps of current. So for this much of amps of current and this much amount of electrolyte is required. And electrochemical machining is supposed to machine a different metal and alloys at optimum machining conditions and with varying requirements of accuracy surface structures. So the accuracy and surface texture, it is not common for all the requirements. It may be different for different conditions for different components. So based upon those requirements, you know, so in those situations, a single tank system is not recommended because of loss of time and wastage of electrolyte during the drilling, clean, cleaning, mixing, or filling of new electrolyte into the tank. It's a time waste process. So it results in automatically the higher cost and poor accuracy of electrochemically machined surface. So we are not going to get very good surface finish. And the two, the poor control of operating conditions also. So more than one tank, therefore, more than one tank, therefore it can be used and their number would be depend upon the range of electrolytes needed to meet the workload. So in some cases, we may require some more amount of electrolyte. In some cases, we may require some less quantity of materials. Depending upon requirement, we're going to supply the different quantity of electrolyte towards the machining zone. Based upon that one, so for in order to meet all these things, we need to maintain minimum 2 reservoirs. Then coming to the tool and tool feed system. So as we discussed, whatever the electrolyte using in this electrochemical machining process, it is having some corrosive nature. So whatever the tool we are using in this machining zone, that tool should be made from the anti-corrosive materials. And tool fixers are also must be anti-corrosive materials. Then only the tool or tool workpiece fixers, the tool fixers are also may have long life. The high thermal conductivity are the main high electrical conductivity and high thermal conductivity is the important things required while preparing the tool or while selecting the tool materials and tool feed system also. Tools, especially tools. And one more point is easy machining of the tool materials. These are the two important points we have to remember while selecting the tool material in electrochemical machining process. First one is the thermal conductivity or electrical conductivity, and it should be easily machinable. Means if the complicated profile, if you want to create a complicated profile on any workpiece, you need to prepare first the complicated cutting tool. The same shape of the tool we have to manufacture. If the hardness of the tool is more or if the machinability is less, then it is very difficult to manufacture such a complicated cutting tools. So if the the tool material hardness is less, if it is easily machinable, then the complicated profiles can be easily machinable, and those complicated cut profile tools can be used to reproduce on the workpiece. Like aluminum, brass, bronze, copper, carbon, stainless steels, and monel are the few of the tool materials used for this manufacturing of the tools. Further, those areas on the tool where ECM action is not required, means the sides of the tool should not require any machining. Machining action is not required. You should not create any machining process so that it should be properly insulated. For example, the lack of insulation on sides of the die sinking tool causes the unwanted machining of the work and a result in loss of the accuracy of the machined work. So from the sides, we should not require any machining process. So the sides of the tool is properly insulated by means of the insulating material. The use of non-corrosive and electrically non-conductive material for making of fixer is recommended. So this fixer should not be a conductive material. It should be a non-conductive material or non-corrosive material. So for proper holding of this cutting tool, but the cutting tool should be a conductive material and it should be an anti-corrosive material. And also the fixers and tools should be rigid enough to avoid the vibration or the deflection under high hydraulic forces to which they are subjected. So during this machining process, we are going to supply this electrolyte with high hydraulic force so that the system should not be damaged. It should be enough to withstand the forces which were exerted during the electrochemical machining process. Now coming to the workpiece and work holding system, the only electrically conductive materials can be machined by this process. The main drawback of this electrochemical machining process is it should be used for only electrically conducting materials. It should not work or it cannot be used for the non-conductive materials. So the chemical properties of the workpiece material largely govern the metal removal rate. The work holding devices here that is related to the workpiece, and the work coming to this work holding system, the work holding devices are made of electrically non-conductive materials. So the work holding system should not be a conductive material. It should be a bad conductor or insulator. But the main purpose of this work holding device is to hold the workpiece properly without moving during the machining process. And it should have good thermal stability and low moisture absorption properties. For example, graphite fiber reinforced plastics or perpex or some of the examples of this non-conductive materials which can be used for fabricating the work holding devices. Now coming to the process parameters. These are the process parameters we are going to use in this electrochemical machining process. The power supply type, DC voltage of 30 volts and current is of 40,000 amps. The current density is of 500 to 20,000 amps per centimeter square. Now coming to electrolyte type, it may be NaCl Sodium chloride, Na nitric acid, NaNO3 are proprietary mixtures, depends upon the requirements, and temperature is in the range of 26 to 50 degrees. And the flow rate is 16 liters per minute to 20 liters per minute. Now coming to the velocity, with how much velocity we have to supply this electrolyte means 1500 meters per minute, and it may be 3 to 3000 meters per minute. This much velocity we have to, with this velocity we have to supply this electrolyte towards the machining zone. Coming to this inlet pressure, it may be a 2200 kilopascals, and outlet pressure is somewhat it is reduced after the machining, the 300 kilopascals. The working gap is in between the tool and workpiece, that is the inter-electrode gap is 0.075 to 0.75 mm. This much a micro level, a very small level gap we have to maintain in between the tool and workpiece. And the side over cut is, it may be 0.125 mm to 1 mm. The feed rate is 0. Means workpiece feed rate is 0.5 to 13 mm per minute. The electrode materials are, the means tool materials are maybe copper, brass, or bronze, like that materials. The tolerance obtained in this, we can maintain in this machining process is 0.025 mm to 0.05 in case of the 2D, two-dimensional components, 0.025 mm. And in case of the three-dimensional components, we can maintain 0.05 mm. And roughness is of 1.5 microns. Then coming to the applications of this electrochemical machining process, it can be used for different purposes in different conditions and different requirements. Used to make disc for turbine rotor blades made up of high strength temperature resistant alloys. It can be used for slotting of very thin walled collets, and it can be used for copying of internal and external surfaces, cutting of curvilinear slots, machining of intricate patterns, production of long curved profiles, machining of gears and chain sprockets, production of integrally bladed nozzle for the use in diesel locomotives, production of satellite rings and connected rods, machining of thin, large diameter diaphragms. Then this electrochemical machining principle has been employed for performing a number of machining operations, namely turning operation, trapning operation, broaching operation, grinding operation, fine hole drilling operation, die sinking operation, piercing operation, deburring operation, and plunge cutting operations. For all this purpose, we can use this principle. And this electrochemical machining can also be used to generate internal profile of internal cams. Now coming to the advantages of this electrochemical machining process. This electrochemical machining can be machined highly complicated and curved surface in a single pass. That is the main advantage of this electrochemical machining process when comparison to the conventional machining process. A single tool can be used to machine a large number of pieces without any loss in its shape and size. So the tool wear is very less when comparison to the workpiece wear rate, so that the life of the tool is very high, more when comparison to the conventional machining process, so that a single tool can be used to produce more number of workpieces. That theoretically the tool life is very high. The machinability of the work material is independent of its physical and mechanical properties. So irrespective of their properties, it can be machined any complicated profile. And the process is capable of machining the metals and alloys irrespective of their strength and hardness. Even though it's high strength materials, even though it's having very high hardness materials, but if it is a conductive materials, yes, you can create any complicated profile on those components. The machined surfaces are stress and burr free, having good surface finish. This is the one more advantage of these components which were produced by electrochemical machining process. No stress will be induced in those components and no burrs will be formed, and that too they are having very good surface finish also. And it yields low scrap when comparison to the conventional machining process. The scrap rate is less and almost automatic operation, low overall machining time, and reduced inventory expenses. It means we need that to maintain a huge number of inventory in the godowns. in order to supply it to the customers. Whenever the customer order comes within the required time, we can manufacture by means of this electrochemical machining process. And there is no thermal damage and bar free surface can be produced. This is also one more advantage. The temperature which were produced during this machining zone or machining process is less, so that no thermal damage is taking place in the workpiece, and that too bar free surface can be produced. And coming to the disadvantage of this electrochemical machining process, the first one is high capital investment is required in order to establish those equipments. And design and tooling system is complex. So the tooling system which is required or which is involved in this electrochemical machining process is a complex. So that its design is somewhat complex. The hydrogen liberation at the tool surface may cause hydrogen embrittlement of the surface, and because of this hydrogen which was liberated at the tool, because of that one, hydrogen embrittlement maybe takes place at the surface. That is also one more disadvantage. The spark damage may the spark damage may become sometimes problematic. So if any sparks develop, there is also somewhat problem. Fatigue properties of the machined surface may be reduced as compared to the conventional techniques. So the fatigue strength of the components which were produced by this ECM is 20% less than that of the conventional components. The non-conductive materials cannot be machined, as we discussed already. It is only useful for the conductive materials. If it is a conductive materials, irrespective of their hardness, is irrespective of their strength, it can be cut any material. The blind holes cannot be machined in solid block in one stage. That is also a drawback. The corrosion and rust of ECM machine can be a hazard, because as it is working with the corrosive electrolyte, is the corrosion is the main problem, rust and corrosion. The space and floor area requirement are also higher than the conventional machining methods. There is also somewhat one of the disadvantages. Space requirement is more. Some additional problems related to the machine tool requirements, such as power supply, electrolyte handling, tool feed. These are some of the problems are there, but we have to overcome those problems by means of the high surface finish, metal removal rate, and we can produce any complex profiles by means of this electrochemical machining process. Thank you to one and all.